In this video, I'm going to be describing how to find the average value of a function, and it's closely related to the mean value theorem for integrals. So first, let's talk about the mean value theorem for integrals, which leads us into our equation to find the average value of a function. So if you remember, the mean value theorem for derivatives said that at some point or some input makes the instantaneous slope equal to the average slope. So since derivatives are talking about slopes, and we're just talking about integrals in this situation, integrals are talking about area. So the mean value theorem is similar, but just talking about area. So at some point on a continuous function in a closed interval, there must exist an input, which we're going to call C, that makes it so that the exact area or the definite integral is equal to the average area under the curve. We could visualize it. If I want to find the area under this curve and I use a left endpoint to do that, well, that would be an under approximation. If I wanted to instead use the right endpoint, I would get an over approximation. Well, the mean value is saying I want something right in the middle of those two things. I want my over approximation and my under approximation to cancel or balance each other out so that I get the actual area, the exact area under the curve. And so the mean value theorem is saying that at some point there is an input that I could plug in where the exact area is the same as the average area. How do we find that average value? Well, we take that mean value theorem and we just divide both sides by b minus a. And now we can find the average value of a function. So f of c is representing the output, the average output, which we can find by substituting values into this equation. This is the sigma notation version of the average value. So you can compare similarities if you understand sigma notation. But I'm going to use this formula right here to do the following examples. So there are always two main types of questions that we may be asked when dealing with average value. The first is find the average value. It's pretty straightforward. The second is find the inputs that make this true, that make the average value equal to the exact area. So let's do the first type in this example. Find the average value of this function. So we're just plugging things into this formula. We're given a function, we're given the interval, so we can plug things into here and evaluate. So my b value is 4, my a value is 1. So 1 over b minus a is 1 over 4 minus 1, which is 1/3. I'm going to integrate this function, so I need to find the antiderivative first. So the antiderivative of the function is x cubed minus x squared. And then I'm going to evaluate it at the upper and lower limits and subtract those two values. So because I'm distributing this 1/3, I'm just going to pretend that I'm dividing by 3. So when I plug 4 in, I'm going to do 4 cubed minus 4 squared and divide by 3. And when I plug 1 in, I'm going to get 1 cubed minus 1 squared and divide by 3 and subtract that from my first value. So 4 cubed is 64, 4 squared is 16. When you subtract that, you get 48. 1 cubed minus 1 squared is 0, so I'm subtracting 0. So 48 minus 0 over 3 is 48/3, which becomes 16. So what does that represent? That represents the average output, the average value of this function. But visually, it also represents the average height of the rectangles that I'm using to find the area under the curve. Let's try out that second type of problem. Find values that satisfy the mean value theorem, or find inputs that make it so the average value equals the exact area. So we got our function. Let's go back up and visualize that problem that we're trying to solve right here. I have my function, and I'm setting it equal to the average value. And we're going to find inputs that make this true. So using the same situation from that last problem, same function, and we've solved for the average value, so we're going to use 16. So I'm setting my function equal to the average value and trying to find those inputs that make this true. So we could subtract 16 from both sides, so we can set our equation equal to 0, and now we can solve this quadratic. You can solve it using the quadratic formula. There's a few different factoring techniques you can use. I'm going to use a factoring technique called regrouping. So I want to find factors of 16 times 3, or factors of 48 that add up to -2. And I know that that is -8 and 6. So I'm just breaking up this middle term into -8x plus 6x. That's -2x. And now I can regroup. So I can factor the first two terms here, factor out an x, and that leaves behind 3x minus 8. And I can regroup these last two terms and factor out a 2, and that leaves behind 3x minus 8. As long as I have the same factoring pair or factor right there, I can factor out 3x minus 8, and that leaves behind x plus 2. So now we can just look at this to find the zeros, or we could solve each of these equations by setting them equal to 0. So if I add 8 and divide by 3, I know one of my solutions is 8/3. If I substitute a -2 here, that creates a 0, so I know that -2 is also a solution, but -2 is not on the interval that we are using or focusing on. So we're not going to worry about that solution. So the solution is 8/3. That is the input that makes it so that my average area and my exact area match. One more example. Sometimes we just need to use our calculator because of the function or because of the difficulty in evaluating it. So we can set it up and we could start to solve this problem. If I want to find the average value of this function on this interval, we're just using our average value equation. And then when we get to the stage where we have to find the antiderivative of tangent is the natural log of secant. It also has a separate form. It could also be the opposite of the natural log of cosine. So there's a couple of different ways to do it. This way may be a little bit easier to do on paper. This we may need to do a little bit more work or just use our calculator. Either way, in this case, it's just much easier if we just evaluate this on our calculator. So the way to do that is to ignore the 1 over b minus a first. Just evaluate your definite integral and then divide it by pi over 4. So that's what I did, and we got this decimal value that we're going to round to 3 decimal places. So there's average value of a function, or to find inputs that satisfy the mean value theorem.